right. Also, hello everyone. Thank you for standing by and welcome to the BSI Subspace tutorial talk series. This event is co-sponsored by the Center for Translational Research and Neuroimaging Data Science and the IEEE Signal Processing Society. It is my privilege today to introduce our speaker, Dr. Mite Mihalkov. Dr. Mihalkov is a good friend and a senior member of the BSI Subspace Volunteer Corps. And he's also a postdoctoral researcher working with Dr. Joana Pereira at the Department of Neurobiology, Care Sciences and Society at the Karolinska Institute in Sweden. He obtained his PhD in material science and nanotechnology from Bilkent University in Turkey, studying the emergent collective behaviors from the interaction of autonomous mobile individuals. Currently, he uses complex networks to model brain connectivity patterns that arise from interactions between distributed brain regions. His goal is to design efficient and sensitive methods to understand the alterations of complex brain networks in individuals with neurodegenerative disorders in order to achieve earlier and more accurate diagnosis, identify patients with worse prognosis, and assess the effects of treatment on brain connectivity. And today he will be presenting a tutorial on BRAPH 2.0, software for brain connectivity analysis with multilayer graphs and deep learning. Mite, you have the floor.
Yeah, thank you, Rogers, for the nice presentation, and thanks really for inviting me to share this software, what we have been doing, through probably the past 2 years, I would have to say. If I could get your okay that you can see the screen and everything.
Yes.
Thank you. So yeah, so
actually, if you can click on hide so that we don't.
Oh, you see also that one.
Yes, yes. Thank you.
Sorry. Sorry. Yeah. So yeah, thanks again for inviting me, and also thanks for everyone, for being here and for showing an interest into this presentation. And here I would present the second installment of a software that we designed in 2017. And I would try to go over its advantages and what we actually changed and what we improved in this software. So at the bottom of everything, this software will be a software for the analysis of the brain and different systems, basically as a complex networks. And as you can see here, it's basically that brain is now very modeled as a complex network at very different levels. And at the heart of this type of modeling, it's this similar this pipeline where you obtain your data with using certain neuroimaging or a different modality. And then you define the nodes that you want to have. You define several connections between the nodes, which constitute then the whole network. And then finally, at the final step, you analyze this network and you try to see whether a treatment or a disease or any like case changes something in this brain, in these connectivity patterns. So I will go just very quickly over the different steps of this pipeline. So for this type of analysis, at the first step, one would have to design the nodes of the complex networks. And in most cases, nodes represent brain regions, but of course they can also represent, like, for example, resting state functional networks, or anything that can be analyzed within this framework. The only there are several constraints about this representation is that preferably this type of brain atlas should cover the complete brain. Obviously, the nodes should have some intrinsic consistency so that they should be defined based on certain knowledge about how that region or that system works, and they generally should not overlap with each other. And you can see here on the right on this figure that there have been a lot of literature has been dedicated to actually solving this issue, and there have been different ways to define the nodes in the brain. So after defining the nodes, we need to define certain association between them, And the basic idea here is that how are we going to define the strength between node A and node B in this figure? And in neuroimaging in general, there has been three ways that has been proposed depending on the imaging modality that has been used to get them. So one can distinguish between anatomical connections between the brain regions, which is termed structural connectivity. Then one could say obtain with functional fMRI, a functional connectivity time series for each node. In that case, the edges represent the statistical dependence between these time series. And then finally, we have effective or directed connectivity, which basically measures the influence that one system exerts over the another. And then after all the nodes has been defined and the associations have been defined, you compile every pairwise association in a given network that is now used to model the connectome or the connectivity pattern of the brain. And in this network, every row and column correspond to the different nodes, and um, every entry in this matrix corresponds to the edges weights. So most commonly, what one would get is this type of weighted matrix where each entry would range between -1 and 1. But then what has been also proposed is that, and it's very commonly used these days, is that instead of analyzing this dense weighted network, one could actually basically threshold the network, in which case it eliminates the spurious connections, and then analyze the binary network, where you either have an edge or not, whether its weight exceeds a certain threshold. And then this is commonly analyzed as a function of this threshold, or the threshold can be chosen so that the density of the connection is constant between the groups. So after this network has been defined and after this analysis has been defined, then there are several graph theory measures that can be implemented, and that they can actually measure the level of integration, segregation, or centrality in this type of networks, and basically make a prediction of which node is more important for the good functioning of the network. Now, in order to deal with all of this step of the analysis, in 2017, we published BRAPH, which stands for Brain Analysis with Graph Theory. And this is a software that comes with graphical user interfaces that guide the user through all of these steps of the analysis that I mentioned to you before. It was also able to perform longitudinal analysis, and it had very different options for visualization and statistical analysis of the data. And again, these GUIs were kind of starting from defining the nodes of Brain Atlas. They went to defining a cohort, and then finally there were series of GUIs that were allowing the users to choose their parameters and to basically perform the analysis, calculate the measures, visualize the results, and perform some statistical inferences on these measures. Now, the problem in the recent years arose that the technology has been improving, the ability to acquire data has been improving. So therefore, now there are very widely available, high resolution, very large data sets that could be analyzed. And with this availability comes the problem that now every different group needs customized workflow. They want to analyze some different perspectives of this brain connectome. So therefore, one fits all software, we thought that it was going to be slightly obsolete because we need something that can be adaptable to the needs of the different users. And to solve these two problems, we have basically set out to apply an extensive change, basically rewriting the software from scratch. We changed the software architecture of BRAPH, and we provide several workflows that introduce state-of-the-art methods that are used currently, so that we provide something for the users to use, but we also provide them a platform where everything can be customized. And this software, which is the second version of BRAPH, will be the main topic of the rest of my presentation. So I will keep most of the time speaking about BRAPH 2 and giving you an overview and give one example of how to design a new analysis in here. But then very shortly, I will just mention three particular works that are implemented in BRAPH2, and then we have used the software in order to publish this analysis. So let me start with the first point, and you see that this is the initial graphical user interface. And one of the different things that comes with BRAPH2 is that every single analysis pipeline is basically organized as a sequential workflow. So therefore, every pipeline is unique and every pipeline is optimized for a specific purpose. So for example, if you look at the first one that I have selected in blue, which is the workflow connectivity analysis BUD, this stands for an analysis where you would provide, the user would provide ready matrices, one matrix per subject, and the user would like to analyze these matrices using binary undirected graphs, and the comparison between the groups would be done by fixing the density. And this analysis will perform this specific purpose, and then we provide 20 to 30 different workflows for which user can choose some suitable purpose for their work. So we are preparing currently extensive tutorials for both developers and end users. And then after everything is completed, all of these tutorials will be posted on the web page, and it will provide a really step-by-step analysis of how both developers and just end users who want to just use the graphical user interfaces could actually deal with their analysis within BRAPH.
Hey, Mite,
yes,
may I interrupt you real quick?
yes.
I think this is a good point here to ask a couple of the questions that already showed up in the chat. People are asking, Jens Schwarzbach was asking about the tutorial videos that they seem to be down, or he was asking if maybe it was a problem on his end.
Yeah, so I was actually coming to those in a couple of slides, and the point
Oh,
is
sorry
that
about that.
so let me just answer. So we have finalized BRAPH from the developer point of view, so everything can be done command line. The tutorials that we would like to post are going to be concerning the graphical user interface first, and then the developer tutorials would come afterwards. And we are planning to start posting tutorials starting from the summer, because we still have to iron out several things in the graphical user interface part. We are still designing the interfaces to be able to allow the users who don't want to program to actually use the software. Currently, the software is usable only from the command line.
Got it.
So
Thank
yeah,
you.
that's why it's a slight delay, and that's why, for example, I will spend a bit of time explaining actually how to program it rather than how to use the graphical user interface.
Got it. Got it. So we had another question about directed versus undirected graphs. I think it's clear that you can the software can process both. And one last question is about can BRAPH 2.0 take from DICOM starting point, or the matrix inputs need to be already processed outside?
So at this moment, it cannot. At this moment, you need to have either time series, either to calculate either time series or the matrices per subject, or eventually maybe to calculate covariance structural MRI time series. But the images currently cannot be imported directly to the software. However, the software potentially could be extended to do so just by switching several parameters. However, due to the fact that the softwares that already do this are well established, the pipelines are pretty much well established and everything, we thought that it's better to provide like to start the analysis from the one level up rather than this, because we felt that people would like to use the established softwares for that particular point.
Awesome. I think it actually makes sense. And thank you for the answers. I'll stop here. You can
no problem. No problem. So just as one advantage of BRAPH2 is that BRAPH2 will features a lock-in system, and this is basically that all results, and this is down to the random seed generation, where the permutations, when you calculate the permutations, like what subject was assigned to which group during each different permutations, they're all saved. So what we imagine here is that a pipeline can be saved and the pipeline can be exported in a single file. And for example, if one is submitting a manuscript using BRAPH2, the idea here would be that BRAPH2 file could be submitted as a supplementary data together with this, so that the referees, the reviewers, they have the complete overview of what has been done. But also, because all the parameters are saved, other people would be able to know which data, which parameters. So basically, this promotes reproducibility and really traceability of the results, so that we know what has been done in each step of the analysis. The big advantage of the architecture is that BRAPH 2.0 is written in Genesis paradigm. And the idea here is that we are going to provide you the code that generates BRAPH. You would need to compile the code in MATLAB, which takes around 5 minutes, but you do it once and then BRAPH is done, and then you can use BRAPH as usual. The big advantage of this is that in this case, you could just by changing several parameters, maybe several files in this code, you can immediately have an object or an analysis pipeline that is immediately integrated into the rest of the BRAPH. And actually what we are optimizing in this moment is that the graphical user interfaces should be automatically generated, even if you consider a new pipeline. Granted, it would be a very simple graphical user interface, which would allow you, simple options, but nevertheless, that pipeline will be fully usable also from this point of view. And just as several things that we imagined that a person could change in BRAPH is that you could add some custom pipeline. If you want implemented a network measure, that could be very well implemented in a very quick time. Then, of course, a different statistical methods or different covariates could be added or removed from the analysis as the user wishes. So therefore, this type of paradigm provides the ultimate flexibility here that everyone could basically write several things. And again, here that the tutorials of how to write all of these things will be posted on the web page, and we expect that this should be done over the course of the summer, so that from September we should be going public with the software. And again, for users who don't want to program and who don't want to have this type of new analysis, we provide several standard workflows that could analyze diffusion tensor imaging, structure and functional MRI data, and the state-of-the-art method that supplement the standard methods, where we have the multilayer networks, directed connectivity networks, and also neural networks that can be used for classification or regression analysis. So the website will be braph.org. And there are already several tutorials, several explanations mostly about the theory underpinning these state-of-the-art techniques. But we are going to be progressively adding more and more things, and we hope that in a couple of months everything should be fine and ready to go. And yeah, the stage that we are at is that we are optimizing the GUIs, designing the outlay, but also optimizing for quickness, for fast calculations, and so that the GUIs come automatically after a new pipeline has been developed. So several words about how to develop new functionalities. So in this small example, I will basically show you how we have developed the functional delayed correlation, which is marked in blue, and all the other folders are the pipelines that are already in the software that we will provide. So functional delayed correlation, for the purposes of this example, is the new pipeline that I'm going to show you how to develop. And the basic idea is that you need to copy only 4 files in order to develop a new workflow. So the BRAPH2 files, which is the 3rd and 4th file on the picture on the right, they manage the graphical user interfaces that are associated with the pipeline, and then they can just essentially be copied in the folder, and you do not need to change anything unless you want some different graphical interfaces. The gen file, which is the first file there, manages the pipeline, and it actually defines the graphs and how the matrices will be calculated, what would be the input data, and the example performs the analysis, calculates the measures, performs the statistical comparisons on the command line. So to show you an example of this analyze ensemble file, so there are 5 parts of this file, and I will show them one by one. So in the first file, in the first line, you would need to define the type of analysis. And in here, we define the analysis as ensemble. And this basically means that you expect each subject to be associated with a network, with a measure. And this defines the way that statistical comparison will be performed in the future. Then one would need to define several properties of the pipeline. And here we have put as properties the repetition time for the fMRI. We have put, these are optional properties, but this is the minimum and frequency value, maximum frequency value, in case you want to further filter out the time series. And because we are going to do a directed functional correlation based on temporal delays, we put the delay value as a parameter that needs to be done in order to calculate these matrices. Several properties more could be defined here at the top of the file, which is basically how to deal with the negative rates, whether to set them to 0, to absolute value, and so on, and which correlation to use, maybe Pearson, maybe partial Pearson correlation, or Spearman. So then at the final 2 chunks of data, you define the subjects and what are the properties of the subject. And in this case, we have defined the subject as a subject fun, which basically means subject functional connectivity. And in this case, what it tells to the code is that we expect for its subject time series. We expect the time series will come to this subject and then go ahead and calculate the JSSA matrix from that one. In the next step, we just need to say that because it's a directed, analysis, we just need to specify the graph as a graph WD, which in BRAPH stands for weighted directed, and then all the measures that have been associated with this graph are automatically available for the user to calculate. This is an optional case. I just put it there to show you that it could be done, and this is just basically a simple filtering out of certain frequencies that you can, but you need or doesn't need to do depending on your analysis. But this is a short code which basically tells us, I have put it here, how to calculate this delayed calculation. So in this chunk of code, we are basically calculating the matrix for each subject. And then finally, at the final step of the code, we say that the comparison will be compared by doing ensemble, which is again, permuting the subject, so that we expect each subject to have a measure associated with himself. So here I need to stress this point that these objects like analyze, ensemble, the subject, the graph, the compare, they're fully implemented into the software, and you actually don't need to implement them again unless you want something different. So this means that from the code that I showed you, around 70 to 80% was copied from the existing pipelines, and what we actually needed to do is to write our code for delayed correlation, which is the method that I showed you, and we just had to specify the graph where we substituted U and D, the letters. But that was basically all the work that needed to be done, and now we have a completely different pipeline that can analyze directed networks, and there is an associated graphical user interface with it. And when I implemented this pipeline, it took around 2 to 3 hours for doing everything. So this is really the fast development that I was referring to before. So just to mention here is that there are 3 chunks of codes that will come together with BRAPH, which is basically the connectivity one, which expects each subject to have a matrix associated with itself. So if you calculate your matrix from outside software, you can input it in BRAPH, and then everything will be associated accordingly. Functional is a pipeline that takes time series of a subject as an input, and then it can calculate the matrices. And of course, you can see here that each of these pipelines has a multiplex and multi-layer and neural networks associated with them, so they can be used in classification. And finally, structural refers to structural covariance networks, where you take structural MRI and then you average across the group. So here, each group will be associated with a single matrix. And then finally, from this part of my presentation, this is so the first part. This is an example of how to perform analysis in the command line. So in the first part, you want the Craddock Atlas. In the second chunk of the code, you would want two groups from XLS file. And here, a pop-up window would come where it would allow you to do this loading of the groups. And then finally here, you define two ensemble analysis. And this just basically tells the code to just do the permutation test as in, permute the measures in this case. And then finally in here, I have calculated the in degree and average in degree. And I have compared the in degree with 10 permutations between the two groups. So this is everything that you need in order to create a new pipeline and run the pipeline on the command line. And when we come to the GUIs, to the graphical interface, if you write BRAPH to GUI on the command line, this interface will pop up. And you can select any one of these analyses, which will make the interface on the left come out. And you can see the interface of the left is already logically arranged so that it guides you toward the steps, and it allows you to do one step at a time. So in this case, one could click on the brain atlas and try to export the atlas from XLS. And this is what will come out. And I'm showing you this because the brain atlas interface is the only one that is almost 80 to 90% finalized. And it will look like this, where on the left panel, you can manage the different regions of the atlas, change their name, order, and if you wish, change the coordinates. On the right, there will be a special panel where you can set everything inside the middle panel. So basically, you can set the view, you can set the color, either background, the color of the spheres, the color of the brain if you wish to have it, but also you can change the surface of the brain. And we provide, in addition to the human brain, we will provide different animal models. Several surfaces are available so that for people who would do this type of analysis, you can also visualize your results on this type of the surface. And one of the most important parts for research is that these figures can be made as beautiful as you wish. They can be made publication ready, and they can be actually exported as a vectorial in a vectorial format that you can put in your in your preferred imaging software, and basically have already publication ready figures out of this. The only feature that remained exploring here is to be allowing them to plot the brain regions as a surface patches rather than as a spheres that are plotted now. And this interface would be finalized. And we are currently in the process of finalizing the rest. So
Hey, Mite,
yeah,
this is looking great. I do have one question that I think is relevant for this section up
okay.
to this point. And this is more like related to the case of comparing with other methods.
Mhm.
Is there a plan to provide in that initial GUI uh, options for pipelines that will like specifically mimic or replicate the defaults of some other brain analysis tools?
Uh, so we were not thinking about that, to be honest. But if it's needed, we can definitely, implement it
Mhm.
in this case. Because the only thing that we would need to know for that case is certain parameters, about the data and the subjects and how the analysis was performed. And then we could create a pipeline that could mimic that analysis, of course, within reason. And here the randomization
Mhm.
from the permutation test, for example, because different seats, different instances would give you slightly different new distributions.
Mhm.
So within what we can fix, we could fix
Mhm.
in that
But
case. And
maybe another option would be to, I don't know, have some kind of forum where people could upload their pipelines. Uh, and maybe have some incentive for other groups to provide their own implementations
No,
of their specific pipelines,
uh,
but for a BRAPH 2.0 interface.
no, exactly. And that's why we developed this. I think I forgot to mention that we developed this on GitHub. So our idea here is that exactly, Rogers, what you were saying, to have a bit of a community, to maybe try to get the people working together. And especially, essentially, a BRAF2 pipeline would be a single file. And in that file, all the parameters will be saved automatically. So from that point of view, I think that the idea that you were suggesting is a brilliant one. That you can have different people. I don't want to use the word check each other's work, but maybe consult each
Mm-hmm.
other's work, verify, and especially in our initial discussions of how to design this BRAF software, our idea was that if you have a data that could be shareable, so that is not subject to these laws that forbid data sharing, then technically you could either scramble it or do something and just provide a single pipeline to the referees, and then referees know what you have done automatically. They just need to
Mm-hmm.
open the file in BRAF2 and they can really check every step of the analysis. And
Right.
it should improve the reproducibility, which is a big problem
Mm-hmm.
currently.
Another thing that I see utility for is when like as a reviewer, you're looking at some results with some customized pipeline and you're familiar with some other different pipeline. Uh, if these pipelines, default pipelines were available, it would be easier to request comparisons, uh, for the review process.
No, you could not. I mean, there is nothing that one could have said it better. Thanks for that. And it really makes a lot of sense. And just to add that we would be very happy to collaborate with anyone who wants to design their own pipelines, and we will be very happy to include them in BRAF, and of course giving the credit where it's due to that pipeline. So of course we would have to discuss it a bit, make certain checks to be sure that it's compatible with the rest of the code.
Right.
But definitely that we are very open for the idea to have different people contributing to this and kind of create a nice collaboration. I think
Mhm.
it's the right word and to do, and hopefully even a specific pipeline which enough novelty, hopefully it can be published, and then this pipeline could serve as a model for that publication, so maybe everything could kind of come together. But of course this is something that we like to do, and we kind of, this is something what we view and what we aim for, and then it's up to also for the people to contact us and to so that we can start the process.
Right. I have one more question here
Yeah.
from Hiddenese. He or she is asking, are there any built-in null models for standardization of graph metrics at any level?
At this moment, what we do have is the randomization. So randomizing a given matrix so that you could create a new model for that matrix. So that we also provide the measures. So if you have your measures for the original graph, then we can provide a new distribution of these measures by implementing what is now very commonly the edge swap randomization of the matrices, so that can be done. And at this moment, these new models are implemented only on this level, where you could analyze so you could export your measures as a real measure, like exported on the graph that you have, but also that measure could be normalized by this average of maybe 10,000 or 1,000 random graphs. And also the significance of that measure could be calculated based on that new distribution. But that's the only one that we have
Mhm.
at this moment.
Thank you. And just to make sure, I have here a question from Armin asking if you, in the following examples, you would have an example that showing how to use matrices as input to perform analysis.
So in the following examples, I was mainly aiming to show you the like what has been done with BRAPH2, just so that I show you that what I spoke until now, it's substantiated. Unfortunately, I didn't prepare in the part of the presentation the one where you input. But if you want and if you are interested in it, I could prepare a short tutorial that I could share with you. That could guide you, step by step of how to do that analysis.
Awesome. So I would just recommend
Yeah,
get in touch with Mite after this talk. Thanks, Mite.
definitely. Thank you a lot. So yeah, as I mentioned, the multilayer, directed, and neural networks are the three main things that we will provide with BRAPH2, and kind of like the three axes that come together with it. So I wanted to show you a couple of the works very shortly in the remaining time that I have, without going to too detail what can be done. So for example, in multilayer connectivity, the idea is that since you are getting now, everyone is obtaining more high resolution data both in spatial and in temporal case, the single analysis, the single layer analysis might not be enough to capture the richness of the brain and how everything works. So therefore, there has been a drive in the last years, which is a pretty novel method, to integrate this information from multiple sources, and this comes the concept with multi-layer connectivity. And it's basically a brain network with more than one layer. Each layer encodes different information, and in its basic case, all possible sets of connections between different layers could be made. Now, while I'm going to show you one study that we did using this type of networks, but apart from the study that I will show you, I'm not aware of any studies that have evaluated the topology of these networks. Instead, what they have been doing is that there is a simplified model of multi-layer where you allow the connections only between the nodes replicas in the two layers. And then you can calculate several measures that we will also provide in BRAPH2, which would give you information about the common properties in two layers that are affected with each other. And just as a simple example, you could calculate participation coefficient, you can calculate clustering or degree overlap. Also, there has been recently proposed a method to calculate multi-layer brain communities, which we will implement. So this one and several more measures will be implemented in BRAPH2. And as a case study, what we did with BRAPH2 that we submitted is that so we used the data of 37,000 UK Biobank participants. And this data is basically the positive and negative connections between 21 resting state networks done with group ECA procedure, which you can see at the left. So then what we did is we split this network into two, and then we created a multiplex and multi-layer networks with this from positive and negative interactions. And our idea was to examine this interaction and whether it plays any role in aging. So what we found out here is that, so in the blue, there is the linear model fitted for men, and in the red is the one fitted for women. We saw that this type of analysis, multiplex and multi-layer analysis, are able to capture the age-sex interaction in the functional connectivity, where they showed us that as we grow older, any sex differences in the connectivity, they basically dissipate over time. And then what we were able to show is that if there are several, so with the several measures, clinical measures and structural measures that were different between men and women, using a partial least square analysis, we were able to show that these measures have a clinical meaning. And there are significant predictors of this type of clinical relevance. And finally, we also showed that these multi-layer analysis measures are associated with different genes, and all of these genes has been shown to actually play a role into the aging process, which again lends credibility to this measure that multi-layer analysis and multiplex analysis are indeed some viable methods that people can explore in their studies. And I will not go into too much, but that was for functional connectivity. one could also create a multiplex connection between two structural modalities. In this case, we did it between amyloid PET and structural MRI modalities, and we showed that this type of construction is sensitive to the progression of Alzheimer's disease. So this was shortly like two case studies that I wanted to show you that concerned the application of multilayer connectivity in BRAPH2. And then I will move in directed connectivity, and I will explain a bit more about the method that I explained when I was showing you the pipeline creation. So in this method, what we have is that consider these 5 regions and consider that with functional MRI, one has measured the time series of this region. Then, because these regions are spatially distributed across the brain, their co-activation will occur with a temporal delay. So what we propose to do here is that we proposed at a given temporal delay, and here when I say delay, I mean time steps between the measurements, and hence there was the parameter D that I showed you in that analysis, that at a given parameter D, we could calculate the Pearson correlation coefficient at that parameter, and we could derive the complete set of correlation in a legged correlation network. So this network is a directed network. The directionality is defined by temporal precedence, so that the region whose time series was shifted to late will be the end of the connection, and the other one will be the source of the connection. The drawback of this one is that you have two connections essentially giving you the same information. So you have two directions, so this might not be that much sensitive. So what we propose to do here is that as this is a square matrix, it could be splitted into antisymmetric and symmetric part. And then we propose here that antisymmetric correlation is the more effective method that can be captured to represent the direction of flow in this functional MRI pattern. And in here, as you can see, this is a sparse network. You have one single effective connection that summarizes both the direction and the magnitude of the functional connection. So this should, in principle, be more representative of the directional character of the functional network. And then we just ran our results. We did this to see if this type of method is sensitive to Parkinson's disease progression. And we completed the analysis with the 4 methods just to see if indeed the antisymmetric matrix is the one that is giving us the best results. And indeed, very shortly, that was the case. We found out that all of the global measures showed differences between Parkinson's disease patients and controls, and these differences in this particular sample were not found out by the other 3 methods. So again, this shows as a case study to just show you that directed functional connectivity networks are indeed sometimes more sensitive to changes into these neurodegenerative diseases. And finally, to show you the neural networks, we will have at this moment, we will have 2 neural network architectures. One is the graph neural networks and also the convolutional neural networks, and they could be used for classification or regression. This regression could be done both on the raw data, and here raw data, I mean mostly the time series, or basically the cortical thickness values for each patient. But this could also be done on the adjacency or connectivity matrices, as well as the measures that would be calculated by these connectivity matrices in BRAPH2. So thanks to Uwe, who I think it's in the audience here, we have done several trials, and this is just one particular trial to show you what BRAPH2 can output for you. So basically, in Human Connectome project, we have taken their data and we have tried to run a sex classification. And what you can see here is that you could have the training process as a function of the interaction, so that you can track how your neural network does the classification, and you can also have these confusion matrices outputted in BRAPH2, and these both were created with the software. So with this, I would like to sum up my presentation. And in most of the presentation, I have been actually speaking about this BRAPH 2.0 software that is software that can be easily developed, that you could think of it as a platform to which users can come and build over it and basically try to implement any single pipeline that comes to their mind. In the rest of that presentation, I was basically showed you 3 case studies that we have developed, 3 pipelines that we have developed in BRAPH 2.0, and the case studies that we have done with the software that resulted in several publications. So this is the team. Thanks a lot to everyone. This is a combined effort between our group at Karolinska Institute, which I show you the pictures of these people at the top, and its collaboration with the group at University of Gothenburg and with Emiliano, Juve, and Giovanni, which are shown at the bottom. Thanks a lot for them, because this was a big endeavor and it couldn't have been done without their inputs and their dedication. And finally, this would be this is the initial page of the forum, of the website. We will be maintaining a forum there. Our aim is to be able to respond within 24 hours to every question that we have, to be able to look at the questions and try to help as much as possible, either by providing some support for the software, but also potentially collaborations where we could work together to implement new pipelines and analyze novel data and novel methods. With that, I would like to thank you for being here, for your attention, and I would be very happy to answer any of your questions.
Great job. Thank you so much, Mite. This is definitely, clearly a big effort that you guys put to get it all together. Really, really nice piece of software.
Thank you.
There are a few questions coming in now. Alex was asking if you can share the complete reference for Garcia et al. I'm not sure
Yes.
what page or slide that showed up.
Yes, I will share immediately.
Thank you.
Just for some reason, I'm a bit, but can I have just a couple of minutes and I can maybe try to answer the other questions in between, because somehow
Yes.
I was not able to locate the paper.
Sure. So the next question is from Georgia Baron, and she's asking, concerning directed graphs, is BRAPH able to deal with both positive and negative weights?
So it depends on the analysis. We can do that. We allow for the people to be able to retain both of the positive and negative one, or set the negative to 0. The problem at this moment arises because several of the measures are not really defined for negative connections, and that's a bit of a sticking point here. In order to be able to do one thing that BRAPH can do, is that BRAPH could allow you to separate the 2 networks and then analyze the networks maybe separate from each other, where you take the negative connections and you analyze the absolute value. In that case, yes, for sure, we could do that, and split also the networks for you. But if you want to calculate some average values, so like a strength, average degree, and all these things, then BRAPH can do that.
Mm-hmm. Thank you. There's a question from before here from Khan Hekmatyar, and he was asking, can we implement these pipelines and models to animals?
Yes, that's the short answer. Everything that I said is transferable to animal models, and I tried to put it that forward because we do have several surfaces. We put several surfaces there that could also allow you to visualize it. However, beyond also the animal models, this could be applied to, for example, we have a work that we applied to dendritic spines in postmortem data. So that's also possible. You could apply to any social network, for example. The reason that I was kind of putting forward the animal models is that we have the surfaces that would allow you the visualization of those models.
Of course. Okay. Let's see.
I can copy into the chat. I found the
reference.
the reference. So yeah, sorry for the late.
No, that's all right. So Jens is again asking, I understand that you're working on GUI issues for the videos, but is there documentation of your API available?
So the documentation is available through MATLAB. If you would go to MATLAB, if you have the software, you would go to MATLAB. You just you compile the software, and if you just write help, for example, element ensemble BUD, it comes a very detailed help that is basically kind of documenting everything that has been done step by step to a great length, so that everyone knows what has been done at which code. We will come in several maybe couple of weeks. We will come with tutorials about development, also developing the software, and they will be there on the website.
Great. Have another comment here. This is from Joshida Majumdar, and she's thanking you for the great talk and asking about the recording for this talk. So that, I guess, is more question for me. So yes, the talk is being recorded and it's going to be made available on YouTube and also through our website here, the PSI. So just stay tuned. We're going to share the link later on, probably next week, at our Slack channels. To get access, you can just register for the BSI and we'll give you access to the Slack channel. Yeah, and Alex, the link to the paper is on the chat if you are listening. There is one more question here from Gael Doucet. For delayed connectivity analysis, how does BRAPH determine the best leg, or do we have to choose it ourselves?
So at this moment, the leg is the input parameter. So you basically choose the leg, and then the whole analysis is kind of taken care of otherwise. The reason for that is that that was the way that we conducted our study, where we were curious to see different legs, so we kind of repeated the analysis several times. But I can imagine a situation where we could also try to have, the maximum leg based on some optimization measure.
Mm-hmm. I'm wondering, is it possible to make, like, for the user to embed that in his scripts, like when he's setting up the analysis?
So,
or is that something that would involve like a more a bigger change in the API that the user would not be able to introduce that kind of optimization?
So yeah, so at this moment we have not thought about that to find the best delay, and therefore everything that I say would be a pure speculation and just throwing out ideas. So I mean, the obvious way to do it with BRAPH is a posteriori. You run the analysis on several delays, and then you optimize the measures that come out. In the software, I suppose that so I have to also discuss if you would like something like that implemented. I'm sure that it can be done, but I would have to discuss with the people who are more involved in writing the software day to day, just to be sure at which level this type of analysis would be maintained. Because I would suppose that this would be like a proxy analysis that would first aim to get the maximal delay before allowing the user to proceed with that delay. So I do suppose that it can be incorporated. It's just that at this moment I cannot on the top of my head tell you at which level it
Mhm.
could be done.
Okay. It seems like other people here are showing some interest in that tutorial that you said you could do for when the user provides the matrices. Um, so maybe I'll leave the suggestion here that when you have the tutorial available, uh, you make it available on our Slack channel. Just notify everyone, and then it would be easy for everyone to access who's interested.
Yes, of course. Probably, yeah. We will prepare it maybe for in a couple of weeks, maybe. Just so that it give us a bit of time to go, maybe 2-3 weeks. But then we can make it available both on the Slack channel and of course on the website.
Mhm. Thank you. There's a question here from Khan again. What version of MATLAB is necessary to run this?
2019B,
Okay.
if I remember correctly. But yeah, that should be the one.
Awesome. And I have here a lot of thank yous for, oh, Emiliano was saying 2020B.
Okay, so I didn't remember it correctly, and he is the one who was more day to day, and yeah, to 2020 be that.
Okay, thank you. And
Sorry
people
for the
are,
misinformation.
no, that's okay. Lots of thank yous for the excellent presentation. I
Thanks a lot.
myself am very grateful. I mean, we are exactly on time, which is fantastic. So I will take the opportunity to start wrapping up. Um, I would again, as we close today's talk, like to thank you, Mite, for the
Thanks a
great
lot.
talk, and remind everyone to follow up on Slack, where we can continue the discussion and ask additional questions. I'm sure there will be many. I will copy all of these questions from today, from our Q&A and the chat into the Slack channel for the record. And other than that, I hope that you all have a wonderful rest of the day. And thank you all for coming by. And
Thanks a lot.
goodbye. Thank you.
Thanks so much. Goodbye.